Welcome to our lecture online, and to get a better feel of how we use the Carnot efficiency concept, here we have a theoretical engine that, let's say it's a gasoline engine. Let's say that it operates at a hot temperature of 800 K, that's the temperature of the hot gas that propels the engine forward or pushes the piston, and the temperature of the exhaust gas coming out. So from that we can calculate the efficiency, the Carnot efficiency, the maximum theoretical efficiency that this engine can have, and then we're going to use that based upon the amount of heat that's being expelled in every stroke, 300 joules, what the maximum work is that this engine can do. So work max is equal to, this is what we're after. All right, so first let's calculate the Carnot efficiency. E sub c is equal to T hot minus T cold divided by T hot, and so that would be equal to 800 Kelvin minus T cold, which is 400 Kelvin, divided by 800 Kelvin, which is 400 Kelvin divided by 800 Kelvin, which of course you can see is 1/2. 1/2 is equal to 50%. So that would be the maximum efficiency that this engine can have. Now, if the engineers were able to obtain that maximum efficiency, and understanding that the heat expelled to the cold reservoir is 300 joules, how much work can we get out of that engine per stroke? All right, we know that the efficiency is equal to the work divided by Q hot. And of course, we don't know what Q hot is. We don't know what work is. But we know that work can also be expressed in terms of Q hot minus Q cold. So let's do that. So work is equal to Q hot minus Q cold, and then we can replace Q hot by, let's see here, if we solve for Q hot is equal to work, and we bring the Q cold across plus Q cold, and that can then go in here. So now we have the efficiency is equal to work divided by work plus Q cold. Now you say, well, I still can't go any further because I don't know what work is, but you do know what the efficiency is. You were given the efficiency to be half or 50%. So let's replace that. So this becomes 0.5 is equal to work max. Now, since we use the Carnot efficiency, we're going to get the maximum work that we could possibly get out of this engine, divided by work max plus Q cold, which was 300 joules. So now we have to solve this equation for work max. So first thing we do is we cross multiply. So we come over here and we have 0.5 times work max plus 300 joules is equal to work max. All right, now we multiply this through, get rid of parentheses. So 0.5 work max plus half of that, that would be 150 joules, equals work max. Since we're solving for work max, we're going to move all the work max variables to the left side. So we have 0.5 work max minus work max is equal to, bring that across to get minus 150 joules. We combine these, so we have minus 0.5 work max is equal to minus 150 joules. And then if we multiply, or no, we should divide both sides by minus 0.5, divide by minus 0.5. This cancels out, and so we have work max is equal to, and that would be a positive 300 joules. So, based upon the Carnot efficiency, the biggest or the best maximum output we can get for the work would be 300 joules if 300 joules of heat are expelled to the cold reservoir. And of course, in reality, you probably couldn't build an engine to be that efficient, so it will be somewhat less than the 300 joules. But that's a good starting point. You know it's not going to be more than that, or even equal to that, because you can't violate the second law of thermodynamics. And that's how you do that.